Hey everyone, welcome to our first video. I'm going to go ahead and go over to our OneNote document. So our first section that we're going to go over is 5.1. This is angles and their measure. When we're talking about angles, the first thing we want to discuss is a ray. So a ray is a line starting at one point and continuing in one direction forever. So an example of how we can draw rays is we can draw them. We always want to have 2 points to define a line, and so the ray will go through that second point. So this is ray AB. Now later in our trigonometry class, we will also go over like vectors, and so rays and vectors, they're all going to work together as well. But right now, we're just kind of focusing on the angle part of it. So an angle is two rays joined at a common endpoint, which we will call our vertex. So an example of this, if I have a ray, let's say it's AB, and then I make this other ray and I call it AC, I've now created an angle right here. And so we might call that angle a couple different things. In geometry, a lot of times you would call it angle BAC or CAB. Most of the time in our class, we're just going to call it angle A. You can also see it called Greek letters, so we will use those a lot as well. So I'm just going to review those for you. So we can also call this angle alpha, and this little symbol I'm drawing right here is just to say that I'm talking about an angle. Some other Greek letters that we're going to use very commonly. So I just said this is alpha. Some other ones we'll see a lot is beta, gamma. Gamma is not as common as alpha and beta. The other one that's super common is theta. So those are the ones that we're going to see in our class. So an angle is actually made up of our two rays that you can see, but they also have other names. So we can call this our initial side. Our initial side of an angle is a fixed ray. So in this case, that's our horizontal part. So my angle A has this initial side of AB of that ray. That's my initial side. What we're going to see a lot in our class is that we're going to have our initial side as the x-axis always. Then we have our terminal side of the angle. And so this is your rotated ray. Now this could still be horizontal. It could be somewhere diagonal. It could be straight vertical. It really just depends. Something really important we're going to talk about is what it means to be in standard position. So an angle in standard position has a vertex at the origin of the xy plane, and its initial side is the positive x-axis. So when we're going to be talking about a angle in standard position, I'm going to draw something for you. So we have our normal xy plane here. So we have x here, we have y here. What we're saying is that the vertex of our angle is always going to be here at the origin, and my initial side is always going to be the positive x-axis. So this will always be my initial side for my angle. Now my rotated ray, or my terminal side, can be anywhere else. Now maybe it lies right on top of the initial side. That's possible. Maybe it's here, maybe it's here, maybe it's straight down like this. It really just depends. And so that's what we're going to be looking at. We always want our angle to be in standard position. There is a little more that will come to standard position, and we'll talk about that a bit later. Now, the degree measure of an angle is the number of degrees the terminal side is rotated. And so if we look at our XY plane, this might take a little bit of prerequisite knowledge. So if we think about a circle has 360 degrees. So if I have my standard position angle, means that I have to start on the positive x-axis. That is 0 degrees. Now if I go all the way around and I create a circle, then I wrap around all the way to 360 degrees. Half of 360 degrees would be 180. So over here, this is 180 degrees. So let's say my terminal side is here. That means that my entire angle is actually from this initial side all the way to this terminal side here. This is also called a straight angle, but this is 180 degrees. If we divide 360 by 4, or if we divide 180 by 2, however you want to think about it, that would mean that this up here is 90 degrees. So if I have a terminal side here, this here is my angle. This is a 90-degree angle. Down here would be 270 degrees. And so again, that means that the angle is this whole piece right here, because we want to always start at our initial side and wrap all the way to our terminal side. You'll also notice that I've been going counterclockwise. So if you are going counterclockwise like this, then this is creating positive angles. Now, if you go clockwise, so if you have your coordinate plane, your XY plane, and you go this way, like instead of going upwards, you go downwards, that'll create negative angles. So if we look here, we would still start at 0. This would be negative 90, negative 180, negative 270, and this would be negative 360. We will talk about negative angles a little bit, but for the most part, there is a way to avoid using negative angles, and I'll show you that later in this section as well. Let's go over some common terms for angles. So I did bring this up already, but we have a straight angle. That is 180 degrees. A right angle is 90 degrees. An acute angle is less than 90 degrees. An obtuse angle is greater than 90 degrees. And then we also have this word for the angles that are on, hard to explain without being able to see you guys, but on the X and Y axes, so your 0, your 90, your 180, 270, and 360. Let me put my degree symbols on here. Those are all called quadrantal angles. And so I may use that word in our content. It's good to know what I'm talking about there. So these are called your quadrantal angles. And it's just because they lie on the X and Y axes. Alrighty, let's go ahead and move to an example. So example 1, I want us to graph the following angles. Just do a little practice here. So part A, let's do 45 degrees. Part B, let's do 250 degrees. And then C, let's do a negative angle. Let's do negative 120 degrees. Sorry, I had to kind of think about it a little bit, what I wanted to do with these. And so in general, whenever you're watching these videos online, you should always pause whenever I do an example. That way you can work the example by yourself, and then you can see whatever I do. So for my 45 degrees, I'm going to draw my coordinate plane, my XY plane. So 0 degrees, 90 degrees, 180 degrees, 270 degrees, and all the way to 360 degrees. So 45 degrees is right in the middle of 0 and 90. So that'll go right in the middle here at 45 degrees. Now 250 degrees is bigger than 180 but smaller than 270. So I'll tell you that right in the middle of this right here is 225 degrees. That is so 250 is a bit bigger than that. So we actually want to get a little bit closer to the 270. Oh. So that'll be more about right here. Now, I'm not super picky about this kind of thing testing wise. So for those of you who are, going to test with me and everything, I'm really just looking for a sketch. So it does not need to be perfect. But if you go ahead and draw 250 all the way over here, that might be a little bit weird, but I am just looking for a sketch here. Nothing extremely perfect, right? Now, negative 120, here we're going to have to worry about the negative angle. So I have 0, and so I'm going to have to go clockwise now. So this is going to be negative 90. This is negative 180. This is negative 270 and negative 360. So negative 120 is going to be between negative 90 and negative 180. So that's going to be about here. Not quite in the middle, it's a little bit closer to that negative 90. So this is negative 120. Something to be aware of is when you draw these angles, you want to make sure that you are going the correct way. So as I go through these, for both my positive angles, I went counterclockwise. For my negative angle, I went clockwise. I went down first. So you want to make sure that you draw it the correct way there. Something else I wanted to go over quickly before we completely move on from here is if the sum of two angles is 90 degrees, they are called complementary angles. If the sum of two angles is 180 degrees, they are supplementary. Supplementary angles are a bit more common to see in our content than complementary, but that is something that will come up later in our classes. We may just run into this kind of randomly, honestly. So that's good to know. Alrighty, now we're going to talk about radian measure. Radians is just another way to measure an angle. It's just a different unit of measurement. So I'm going to write for you the definition. So it says the radian measure of an angle alpha in standard position. So again, standard position just means that the initial side is on the x-axis, positive x-axis in particular, is the directed length of the intercepted arc on the unit circle. And of course, I would like to explain to you, what this means. So first of all, you may not know offhand what the unit circle is. The unit circle is a circle. I'm not sure why my font looks like that. Let's fix that. There we go. A circle with a radius equal to 1. That is the unit circle. Something else I'm wondering if you remember is the circumference of a circle. If you don't, I will write it for you, but circumference is 2 pi r. So let's look at this for a moment. If we have a circle with radius 1, so that means we have circle and it goes through a radius of 1. So it starts in the middle, radius of 1. That means the circumference of this circle, since my r is 1, would be 2 pi times 1, so that's 2 pi. What this tells me is that the radian measure of a full circle is 2 pi. So if I start here at 0 and I wrap all the way around for the circle, I would end up at 2 pi. What this is measuring is how long this is. It's that length of this arc of these arcs that's being created. So in our case, we're dealing with the circle, of course. But when we talk about radians of an angle, and we say this right here, you see this intercepted arc. So let's say I have an angle, let's say right here. So this intercepted arc is this piece right here. So the radian measure is measuring how long that piece right there is. So it's just another unit of measurement. So what you can see here is you see how if I wrap around the entire circle, I get 2 pi. This gives me a conversion factor. So now I know that if I wrap around the circle in degrees, it goes to 360 degrees. If I wrap around a circle in radians, it goes to 2 pi radians. This tells me that 360 degrees is equal to 2 pi radians. Now to make this a little bit simpler of a conversion factor, we can divide both sides of this by 2 and we can say 180 degrees is equal to pi radians. So if I draw my circle in radians, I would have pi over here on the left side. This is going to be important. So anytime you want to switch between degrees to radians or radians to degrees, we're going to use this conversion factor. Now, depending on whether you want to go to radians or go to degrees, will change how we use the conversion. Of course, I'll do some examples though. In general, degrees are used more for like understanding. They're a little bit easier to like visualize. Radians are used more for calculation though. So later we're going to see some formulas, and you have to use radians when you deal in formulas. If those of you who may take a physics course, you're going to notice that for the most part you need to stay in radians if you ever use an angle in like a physics problem or some kind of thing with formula, like a work formula or something like that. It's hard to explain with just, in our sections without having so many applications. But for those of you who maybe are going to take the calculus series, they mostly deal in radians as well. So let's do an example of some conversion. So example 2, we're going to convert degrees to radians. And vice versa. Part A, let's do 210 degrees. Part B, we'll do negative 135 degrees. Part C, we will do pi over 12. And part D, let's do negative 4 pi over 3. So I've got 2 going from degrees to radians, and then 2 going from radians to degrees. I'm going to start off with my 210 degrees. So whenever you use a conversion factor, you basically turn it into a ratio that you can use. So we're going to either multiply by 180 over pi or pi over 180. So if we start with 210 degrees, remember anything can be written over 1 if it doesn't have a denominator. And so what we want to do is we want to multiply by our conversion factor. So if I multiply by pi over 180 degrees, I'll be able to cancel out my degrees and I'll be left with this pi here. That pi is going to mean that we have moved to radians. So as I do this, I'm going to do 210 divided by 180. And so that's going to give me 7/6. And then I just have that pi kind of hanging out. Usually whenever we're in radians, we leave things in terms of pi. You can multiply in the pi sometimes. I'm just going to tell you, though, that we like to leave our answers always exact, so it really is best to just leave it with pi. But this is now in radians. And so again, the reason we put the 180 at the bottom is so that we could cancel out the degrees. Negative 135 degrees. Again, we're trying to get rid of degrees, so we want degrees to go at the bottom, and we want our radian, which is pi, to go at the top. This is going to give me negative 3 pi over 4 once I do this division. Now part C, here, let me label this. This is A, this is B. Let's do part C here. Part C is going from radians to degrees. If you want to get rid of radians, then you're going to have to get rid of pi. So I'm going to put my pi at the bottom now, and I'm going to put 180 degrees at the top. So you'll see the pi's will cancel. And now at the top, I'll be left with my degree symbol. So that's a good thing. That means I've moved to degrees. This is going to give me 15 degrees. So here I'm doing 180 divided by 12, and I get 15. Part D, I have negative 4 pi over 3 times 180 degrees over pi. I get negative 240 degrees for this one. Let's talk about some common angles that we're going to use. You're going to use some of the radian measures so often with the degree measures that it's going to be pretty time consuming if you always have to convert. So sometimes you're just going to want to have certain ones memorized. So let's talk about which ones we may want to have memorized. I'm going to draw in degrees, and then I'll draw in radians. So in degrees, I have 0 degrees, 90 degrees, 180 degrees, 270 degrees, and 360 degrees. Also commonly, we're going to use 30 degrees, 45 degrees, and 60 degrees. So we're going to want to know all of these in radians as well. So if I draw all this in radians, let's see what I get. I already know that 0 is still 0. 360 is 2 pi. 180 is pi. We found that out earlier. Now let's think of this for a second. If half here is 0 to pi, what is half of pi? Don't think too hard about it. It would just be pi over 2. So 90 degrees is pi over 2 radians. 270 degrees is 3 pi over 2. Now your 30, 45, and 60, you're welcome to convert those the long way. But again, we're going to use them a lot, so I'll just go ahead and write them for you. So 30 degrees is pi over 6. 45 degrees is pi over 4. And 60 degrees is pi over 3. It's very important to remember that these are just different ways to talk about the measure of an angle. Later in our course, when we talk about sine, cosine, tangent, and stuff of all of the angles, the angle itself can either be in degrees or radians. That part of it does not really have much to do with the sine, cosine, tangent part of it. Now we'll get there later. I'm talking a little bit ahead right now. But it's just good to know that the degree or the radian, it's just different ways to talk about degree measure. That's it. It's just how big the angle is. Something I also would like to talk to you about is graphing radians. This can always be a little bit of a struggle for students, so I want to make sure we go over this. So graphing radians. I'm just going to make an example out of it. So example 3, I'm going to say graph the following angles. Now, if radians are just terrible for you, you can always convert them into degrees. But like I said earlier, it might become a bit time consuming if you always have to do that. So it's good to be able to just work with both. So I'm just making up a few of these for us to go over. And I will graph them. So part A. Four pi over 3. The issue is, I would really like to see a denominator of 3. That way I can figure out where 4 pi over 3 is supposed to go. So if this is 0 or 2 pi, and this is pi, remember that everything can be written over 1. So this is 2 pi over 1, this is pi over 1. Like I said, I want to see a denominator of 3 so that I can tell where 4 pi over 3 would end up. Anytime you want to change the denominator of a fraction, you can multiply the top and bottom by something. So if I want a denominator of 3, I'm going to multiply by 3 over 3. This is going to tell me that pi is the same as 3 pi over 3. 2 pi is the same as 6 pi over 3. Now again, the reason I've done this is because I have a 3 right here. So I need to see denominators of 3 to figure out where 4 pi over 3 goes. So now we think, okay, is 4 pi over 3 less than 3 pi over 3, or is it bigger than 3 pi over 3? I hope at this point you say that it's bigger than 3 pi over 3, but it's not quite as big as 6 pi over 3. Here's what I'll tell you. 4 pi over 3 is going to go right here. Oh, whoops. Is going to go right here in the third quadrant. Now, how do I know this? The way that I know this is because if I add a pi over 3 to 3 pi over 3, that's how I can get 4 pi over 3. Now, you also might be asking, how did I know that it didn't move into the fourth quadrant? Well, pi over 3 is only 60 degrees. So it's not going to push us all the way into a different quadrant. I'll tell you this as well. 2 pi over 3 is right here. And you can see that that's 1 less than, in the numerator, than 3 pi over 3. Over here in the fourth quadrant, it would be 5 pi over 3. And so we would take our 6, subtract it by 1, and that's how I get my 5. So 4 pi over 3 is in the third quadrant. And just a reminder, that is the entire angle right here. You may also want to know, why did I only look at 0 or 2 pi and pi to figure this out? The reason is because when we talk about standard position, we're looking off of the x-axis. So I don't really care about the y-axis at all, so I didn't worry about drawing it in. You only need the x-axis to figure out where your angles are. Let's go ahead and do part B. So part B, I'm going to draw again. I have 0 or 2 pi, and I have pi. I'm also going to write these over 1 again. Now my denominator here is 4. So I want pi and 2 pi to have denominators of 4 so that I can figure out where 7 pi over 4 would end up. So if I multiply this by 4 over 4, multiply this by 4 over 4, I get that this is 4 pi over 4, which is the same as pi, and this is 8 pi over 4. Now 7 pi over 4 is going to be right underneath 8 pi over 4. How do I know it's not that far away? Well, 8 pi over 4 minus pi over 4 would give me 7 pi over 4. Why did I just say minus? It's because I'm looking from here. I'm looking from here to here, which is subtraction, because we're dealing with negative angles if we go clockwise, so that's why I'm dealing with subtraction right now. Now 7 pi over 4 is not a negative angle, so don't get confused there. The angle here is still, oh goodness, I don't mean to have the eraser on, sorry. Is still this entire angle right here is 7 pi over 4. Now I'll tell you the other ones in the other quadrants as well. So also for a second, just remember pi over 4 is just 45 degrees, so it's not very big. That's why I did it kind of in the middle. In the second quadrant, our angle in the middle would be 4 pi over 4 minus pi over 4, which would be 3 pi over 4. So you see how the numerators are just changing by 1? In quadrant 3, it'd be a little bit bigger than 4 pi over 4. We would just add 1 in that numerator, so this would be 5 pi over 4. Let's go ahead to part C. Part C, I'm doing 5 pi over 6. I'm going to draw again. I have 0 or 2 pi, and I have pi. Both of these can be written over 1. My denominator is 6, so that means I want to multiply by 6 over 6. That way I can see that denominator of 6. So I get 6 pi over 6. Again, that's the same as just pi. And this is 12 pi over 6, which is the same as 2 pi. 5 pi over 6. Is it closer to 6 pi over 6 or 12 pi over 6? Closer to 6 pi over 6. It's also a little bit smaller than 6 pi over 6, so it's going to have to become a little bit before it. So 5 pi over 6 actually lies right here. Let me go ahead and use another color. 5 pi over 6 is right here. Now you also may wonder, why did I draw it so small to the edge? It's because I know that this difference here is pi over 6, which is only 30 degrees, so it's not very big. It's not very far away from pi or 6 pi over 6. In the other quadrants, right here would be 7 pi over 6. I'm just adding 1 in that numerator. Over here, it'd be really close to 12 pi over 6, but just off by 1 in that numerator. This would be 11 pi over 6. And it's coming before the 12 pi. That's how I know it's smaller than. And one more. This one's 7 pi over 3, so I definitely think you should try it out before I do it. This is 0 or 2 pi. This is pi. If I want to write these with a denominator of 3, this is 3 pi over 3. This is 6 pi over 3. So 7 pi over 3 is a little bit bigger than 6 pi over 3. So it's actually going to come after this 2 pi or 6 pi over 3, right? It's bigger than that. So it needs to come after it, which is going to put it in quadrant 1. But it's only one off, so that's how I know it's only a quadrant, either above or below. It's never, it's not going to jump like 2 quadrants all of a sudden if you only went from 6 to 7. Perfect. Now be careful here with this one. This one does wrap around all the way here. So it's circling around the circle. Sounds weird to say, but it's circling around an extra time there. Alrighty, let's talk about our next little piece here. So our next small topic in this is coterminal angles. So let me go ahead and write some stuff for you. So two angles in standard position sorry, let me fix it, with the same initial side and terminal side are called coterminal angles. Some properties of coterminal angles is if the measure of alpha plus 360 degrees times k is equal to measure of beta. In radians, this would look like the measure of alpha plus 2 pi k is equal to the measure of beta, and k is an integer. Of course, let me go ahead and explain kind of what this means. So if you've got two angles in standard position, they have the same initial side. They also have the same terminal side. These are called coterminal. This little definition right here, well, maybe not, I shouldn't say definition, but this little equation type thing that we're seeing here is what it's meaning to say is that if you add 360 to some first angle and you get that second angle, that's what we are going to see with coterminal. Let's think about what it means to add 360 to something. All it means is that you're going to wrap around the circle one whole rotation, but you should end up in the same place, right? So if I have, let's say I have an angle right here. Okay, well, if I add 360 to that, that just means I'm going to go over a whole rotation, right? I'm just going to add 360. But it's going to end up in the exact same place, thus having the same terminal side. That's what coterminal is really meaning. And so we're going to do a little bit of examples with this as well. Now in radians, you would add 2 pi. Let me explain the k for a second as well. The k just means how many times would you like to add it? How many times do you want to wrap around your circle? If you want to wrap around your circle twice, then you're adding it twice. If you want to maybe wrap around it the opposite direction, like maybe you don't want to go counterclockwise, maybe you want to go clockwise, well then you would say k is -1, or you would just subtract 360 in that case. And there's different reasons you might do this. So let me go ahead and give us an example. So example 4, I'm going to say find an angle coterminal to theta between 0 degrees and 360 degrees. Sorry if the audio is a little different now. The original audio cut out at this moment, so I'm doing a voiceover from now on. So part A, we're going to do theta is 960 degrees. Part B, theta is negative 225 degrees. So for part A, we're looking for an angle that is coterminal to our original angle, which is 960, and we want it between 0 and 360. So 960 is just too big of an angle to plot on our normal XY coordinate plane. So we can make it a bit smaller and more manageable by subtracting 360. So if you look back at that definition with the k in it of the at like plus 360k, if we're subtracting 360, then our k is technically negative 1, which is still an integer, so we can do it. So if I do 960 degrees divided by, 960 degrees subtracted 360 degrees, I get 600 degrees. Now 600 is still a bit too big, a little too hard to work with, so we can subtract 360 again, which gives me 240. 240 is between 0 and 360, so that's the angle that we were looking for here. Then I go ahead and graph it at this moment. So remember, we have our 0 degrees or 360 degrees, 90, 180, 270. 240 is going to end up in quadrant 3, and it's a bit closer to the 270, so I kind of draw it that way, just a little sketch. And so 960 and 240 are coterminal, meaning that they have the same terminal side. So when you graph them, they're actually in the same exact spot. It's just that 240 is a bit smaller version of the same angle. So 960 is actually wrapping around the circle twice. I know that because I had to subtract the 360 twice to get between 0 and 360. And now the 240 is only going, not even a full rotation, so it's just a lot easier to work with that smaller angle. Now for part B, the issue is that we have a negative angle. So this is another really common use of coterminal properties, is if you have a negative angle, you can make it more manageable by adding 360, again, to get it between 0 and 360. That way you don't have to worry about like plotting clockwise instead of counterclockwise. You can just use coterminal. So if I add 360, I get 135 degrees, which is going to end up between 90 and 180, which will be in quadrant 2. So 135 degrees is in quadrant 2. So is negative 225 degrees. It's just that 135 is that counterclockwise movement, and then negative 225 would be that clockwise. But they have the same terminal side. They're in the same spot, so they're pretty much the same angle. We call it coterminal though. So those are your most common uses of finding coterminal angles, is just trying to get things between angles between 0 and 360 instead of too big or negative. Now I'm going to do an example using radians as well. So this one says, find an angle coterminal to theta on the interval 0 to 2 pi. So again, 0 to 2 pi is going to be one rotation of our circle. So I'm pretty much saying 0 and 360, but in radians, it's 0 and 2 pi. Part A, we're going to do theta is equal to negative 5 pi over 6. Part B, theta is 13 pi over 2. So for part A, we're dealing with a negative angle. So to make it into a positive angle between 0 and 2 pi, I can add 2 pi. And again, the reason why you want to add 2 pi is because you want to go a full rotation so that you end up in the same spot. A common mistake is people accidentally add pi. So I need to add fractions here. So remember, anything can be written over 1. I'm going to multiply the 2 pi over 1 by 6 over 6. That way I get the same denominator as that negative 5 pi over 6. I get negative 5 pi over 6 plus 12 pi over 6, which is going to give me 7 pi over 6. So that's the angle that I'm looking for. So now I'm going to go ahead and plot that. Remember that pi can be written as 6 pi over 6. 2 pi, it's 12 pi over 6. So 7 pi over 6 is going to be in quadrant 3. It's pretty close to 6 pi over 6. It's just a little bit bigger. Next, we'll do this 13 pi over 2. Since this one, the issue is that it's too big, we're going to make it smaller by subtracting 2 pi. Again, I put 2 pi over 1. That way I can multiply it by something to get common denominators, so I can subtract these fractions. So I'll multiply it by 2 over 2, so that's going to give me 4 pi over 2. 13 pi over 2 minus 4 pi over 2 is going to be 9 pi over 2. Still too big, still not between 0 and 2 pi, so I'll do it again. 9 pi over 2 minus 4 pi over 2 is 5 pi over 2. Again, we're still too big, still bigger than 2 pi. So I do it one more time. 5 pi over 2 minus 4 pi over 2 is pi over 2. Now pi over 2 is the same as 90 degrees, so it's going to be that quadrantal angle up there at the top. Now I knew that I needed to keep going. Like, how did I know when I was smaller than 2 pi? Remember, 2 pi would be the same as 4 pi over 2. So I needed to get an angle smaller than 4 pi over 2. If you're not used to seeing the fractions, it could be a little tricky to make sure that you're in the correct interval. Our next little subsection here is arc length of a circle. The definition for arc length has some words in it that hopefully you'll recognize. This says the length S of an arc intercepted by a central angle of alpha radians on a circle of radius r is, and my equation here is S equals alpha times r. My hope is that you can notice some familiar words. So if you look at that arc intercepted by phrase right there, that's very, very similar to the radians definition. The only difference is that the definition of radians was specific that it was a unit circle, which meant that our r was 1, because that's a unit circle, the r is 1. And then the other thing is that we didn't have a central angle, we were looking at the entire circle, so we didn't have like an angle alpha, we just said it was 2 pi, if you think back to earlier in our video. Now what we're looking at is we have just a portion of our circle that we're looking at. So we're going to have our radius here, and then we'll have some kind of segment on the edge here of our circle. And so we're looking for how long that is. We're looking for its length. So then we need to know how big the angle is that creates that arc that's happening. So that's why we need our alpha, and then we need our our radius as well. Something you'll have to be a bit careful of here is that your alpha is defined as in radians, so it's going to have to be in radians to use the formula. So if you are maybe given your angle in degrees, you're going to have to convert that into radians before you can use your formula. That part is super, super important. Also, make sure that you are actually using radius whenever you do your problem. Sometimes, give you a hint for later, you might be seeing diameter and not radius. Let's go ahead and look at an example. So this says find the length of the arc intercepted by a central angle theta on a circle with radius r. And we're going to be given that our theta is pi over 4 and our radius is 12 centimeters. So we're looking for length of the arc, which is going to tell me I need my formula, S equals alpha times r. Now it already gives me my angle in radians, so that's good. We can just plug that right in as my alpha. And it's because it's a central angle, so just because they changed the like from alpha to theta, it's still the central angle. And then multiplied by 12 for my radius, so I get 3 pi centimeters. I usually leave answers with pi in them, that way it's exact. So I'm going to just draw for you what we're seeing. So we've got a circle, we've got radius 12. My angle's pi over 4. Remember, pi over 4 is the same as 45 degrees, so that's like right in the middle of that first quadrant. And so that purple that I wrote here, that length of that arc is 3 pi. We'll do one more example. This one's example 7. It says the wagon wheel has a diameter of 28 inches and a central angle, well, this one just says angle, that's okay, of 30 degrees. What is the length of the arc S? So again, I'm looking for that arc length, so I'm given my formula, S equals my angle times my radius. But I have a few issues here. One, I'm given not the radius, I'm given the diameter. Now it says diameter is 28 inches. Radius is your diameter divided by 2. So 28 divided by 2, so that's going to give me 14 inches as my radius. So you want to make sure you plug in 14 and not 28. The other issue is that my angle was given to me in degrees. It says 30 degrees. But be careful, to use your formula, you've got to be in radians. So 30 degrees is equal to pi over 6 radians. That's one of those angles that I do expect you guys to remember. If you don't remember it right now, that's all right. You can always do it manually by doing the conversion factor. So 30 degrees times pi over 180 degrees will be pi over 6. Now I'm going to plug everything into my formula, which is going to give me S equals 7 pi over 3. And this is also in inches because my diameter and my radius were also in inches. If you'd like to approximate this, it'd be 7.33 inches. Now we can also see problems where maybe we are looking for the central angle and we're given S and we're given R or something like that. Maybe you can be given S, you can be given your angle, and you're asked for radius. So you could see slight alterations of this type of problem. But that's it for this section. That's it for 5.1. So I will see you all in our next video. Bye-bye.